sound good.
Okay, so this is the last of these lectures, which is really very, very simple, and I'm aware of the fact that most of you typically heard most of what I'm saying. Next week we will have some kind of the problem-solving lecture. Two young colleagues will be taking my place. And in 2 weeks, I will get to another intricate question of competing interpretations of quantum mechanics. Probably will spend one full lecture on that. And this, I believe, will be slightly more, well, not very difficult, but probably less well known to you. Okay, so what we finished with last week was the introduction of a momentum operator, and we did it first looking at translations. We checked, it's almost obvious, that standard quantum mechanical systems, say, moving in one dimension, would have scalar product which is invariant under translations. So translation operator is a unitary operator, and then one can define its generator, and this generator is is 1 over I d by dx. The question of making momentum out of it requires introduction of some constant, and of course by such considerations as ours, to tell how much is this constant, of course, it's not possible. Fortunately, we know that this constant of the dimensionality of action, of the dimensionality of angular momentum, which really pops up in quantum physics, is due to Planck. It's a Planck constant. Now, very similar approach can be used to figure out what is the operator which describes the angular momentum. While momentum is a generator of translations, angular momentum is, of course, a generation of rotations. And if I would take, famous problem of derived markers, if I would take rotations over z-axis, say I make a rotation by angle phi naught, yes, then I can define operator, unitary operator, describing such rotation acting on psi very easily if I would use this, instead of Cartesian, if I would use spherical coordinates. If I would write here r, theta, and phi. Why? Well, because obviously such rotation means that r and theta remain unchanged, and phi is shifted by phi naught, yes? So this operator, still this is not a very good marker. I'm not sure how well it would, whether it would be visible. A little better. So this is, of course, r theta phi minus phi naught. In other words, from this we immediately see that the z component of angular momentum, something which is generating rotations over z-axis, is exactly the same operator as we had for translations, except that with respect to the phi variable. In other words, from this immediately follows that Lz can be written as h bar over I d by d phi in complete analogy with the translations. Yes, we can again think of Taylor expansion and then recognizing that this generator is the differentiation, and again, there's a question of dimensionality. Dimensionality should be that of angular momentum, and we already have at our disposal a nice unit of angular momentum provided us by Max Planck, so we plug it in and that's it. Okay, now one can do one of two things. One can either do a little bit of completely stupid calculations, changing variables from spherical to the Cartesian, to find out how h bar over I d by d phi can be expressed in terms of Cartesian coordinates, but instead one can again refer to the strategy that I am advocating here. Namely, in the Cartesian coordinates, this rotation here is of course given by 2 by 2 matrix, yes? It's a cosine phi naught, sine phi naught, minus sine phi naught, cosine phi naught. That's the rotation matrix. Yes, in xy plane, z. I could write it as a 3 by 3 matrix, but then it would be just 1 in the z direction. Yes. What's relevant is really that x and y are changing while we are rotating. Yeah? This is fine, but it is sufficient for us to write infinitesimal version of this operator. In linear approximation in this rotating angle, and let me call this small angle delta phi naught. This is of course, surely cosine is 1 because in the expansion it's in the second order. This is d phi, this is minus d phi, and this is 1, right? Okay, if we know this, then we can rewrite exactly the same equation, namely u of this delta phi naught acting on psi, but this time in x, y, z coordinates as action of this matrix on this x and y. In other words, this is the same as psi of x plus delta phi 0 y, y minus delta phi 0 x, z. I think you agree. Well, it is enough to know the action of our unitary operator for very tiny delta phi. Why? Because if I would write this operator in the form u of delta phi naught in full glory, I over h bar Lz times delta phi naught, yes? I could plug this knot. It's not necessary if I have delta, yes? It will not be confused, I hope, with the phi coordinate in the spherical. That this is the same as 1 minus I over h bar Lz times phi naught, plus of course, phi naught, delta phi, plus of course terms of higher order. But by expanding this to the lowest order, I can identify what Lz is. Yes. So what do we get? Of course, for phi naught equals 0, I get psi of x, y, z. And then the next correction is plus delta phi times by dy, acting on psi x, y, and z. Plus, of course, terms of higher order. Now, looking at this and looking at this, we can figure out what Lz is in the Cartesian coordinates. And of course, it's a very familiar expression. It's h bar over I x d by dy minus y d by dx. In other words, this times this and this times this is a momentum, so it is x py minus y dx. Of course, expression which is familiar to everyone, but I kind of like this sort of justification for this, yes. That we really see that this operator generates infinitesimal rotations around the axis. Okay? Now we have, very easily, we have derived a formula that is describing Lz, and of course it does not require any additional thinking to write expressions for Lx and Ly. Lz is not distinguished at all. It's been distinguished by our assumption that we rotate around z. Yes? If we rotate around x, then of course there is interchange of x, y, and z. Y around y, same thing. So there are three objects, each constructed this way. And of course, people know, you are well-trained young physicists, that it can be combined to something like R vector product P, so it's exactly the same relation that we have in classical physics. But now these guys are operators. We remember that x's do not commute with p's, that the commutator is I h bar, and therefore various components of L do not commute among themselves. Yes? In particular, let me write one more thing. If I would like to use the indices, then there is a very handy epsilon ijk, completely antisymmetric tensor that allows us to write it this way. Well, of course, instead of x, y, z, I'm now calling coordinates x1, x2, and x3. Yes. Written this way, there is a hidden assumption that repeated indices are summed over. Yeah, so it's a double sum. It's the same, exactly the same expression as it's here. Now, once we have this angular momentum operators, then it is very important to check, and it's easy to check, that they obey a very simple commutation relation. Yes. This is I. I always pops up if we commute two Hermitian operators, as I was explaining last week. Yes. There is h bar, and then there is this last, so to say, L component, which is not present on the left. And again, our epsilon ijk comes handy because it allows us to write it in a compact form. How do I check this? Well, it's very easy. I just plug in here those expressions of L's in terms of x's and p's, and I'm using the basic fundamental commutator. xi pj is equal to I h bar times delta ij, yes? There's one more identity. which has to be remembered very, very, very well, because it is useful. We are using it over and over again, and that's that if I have this sort of commutator, then it is the same as A times commutator of BC plus commutator of AC with B on the right. Whenever we have squares of something, yes, like product of some two operators, then one has to remember about this formula, because using it you can extract, you can reduce everything to these fundamental commutators of basic objects, those that you know. Why is it correct? Well, it's a trivial exercise. Yes. One can write what is on the left, one can write what is on the right, and it happens to be the same. So it's really true. Good. Now, this idea of symmetries, unitary operators, symmetries of the scalar product, and then unitary operators, is very general. We used it for deriving somehow the generator of translations. We used it now to derive the generator of rotations. But if I look at the evolution operator, I see that the same thing applies to this operator. This can be viewed in the same fashion. It can be viewed as the generator, as the unitary operator amounting to the progressing time. Yes? It takes this u of t acting on some vector psi at time 0, produces vector psi at time t. Very much the same way as unitary operator describing translations was shifting variable x variable, like rotations was shifting the angle, evolution operator is shifting time, yes? And then Hamiltonian mathematically plays exactly the analogous role to momentum or to angular momentum, except that with respect to something very different, namely with respect to the time translations. And since very often, universally, both in classical and quantum physics, we are concerned with the evolution, then of course this is much more often used than those other operators. Good. So, now we are somehow equipped. All the, one more thing, one more remark on this general framework. The remark is the following. As we all know, the Hamiltonian for, say, one-dimensional, three-dimensional motion, as in classical physics, is a sum of a kinetic and potential energy, and kinetic energy is, of course, p squared over 2m. We know what momentum is. And potential energy is, of course, function varying some time-dependent fields. It's just a function of position. Yes? And position operator is multiplication and analytic function. If it is analytic function, then of course I can safely write V of R. And this way I I also know how to construct Hamiltonians and then look for everything. Look for the spectrum, namely the set of eigenvalues, set of eigenvectors, and so on. If we are using what in this lecture we stress should be called a Schrödinger representation in position space, then this P is of course second derivative for the 3D is a Laplacian. And every problem, either of solving for the evolution or solving for the eigenvalues, boils down to solving some differential equations. And obviously, probably each of you has been solving such things and will be solving, some others will be solving such things. However, of particular beauty are those quantum mechanical eigenvalue problems that can be solved completely algebraically, that can be solved only using the algebra of commutators. It's particularly nice because you can avoid differential equations whatsoever. And today, my main part of the lecture will be devoted to two such examples. One is quantization of angular momentum, and the other is a quantization of the energies of the harmonic oscillator. Probably you are very familiar with both. It is conceivable, not sure, that one or the other, or maybe both of these problems, you have seen solved using differential equations, which is very good, which is very important. I want to avoid this, and maybe for some of you it will be something, well, new or semi-new. So let's start with the properties of quantum mechanical angular momentum. Quantization. Of the angular momentum. Okay, all we know at the beginning is this relation that we have seen already, yes? K epsilon I jk. And then remembering what we know about diagonalization, simultaneous diagonalization of various operators, that they can be simultaneously diagonalized if and only if they commute, we see that there is no way that we could find common eigenbases of eigenvectors of two components, because two components do not commute to the third component. However, out of this relation, one can easily check that the L square commutes with every Li. Again, you write L square as L1 square plus L2 square plus L3 square, yes? And those two that are not commuting, one of them is commuting, the one here, yes? The other two, you again use this magic CAB formula, you use the commutation relation, and you find out that this fellow is equal to 0. So, even though more than one component cannot be simultaneously diagonal, we could diagonalize simultaneously L squared and one of the Cartesian components of angular momentum. And of course, there is no distinction between x, y, and z, so everyone is taking z. Yes? So in other words, one can look for the simultaneous eigenstates of these two operators. Sometimes I write z, but if I use the synthesis, that is the same as L3, of course. So, let me call, I need two quantum numbers. I need information about the eigenvalue of L squared, and I need the information of the eigenvalue of first one, this information is hidden in quantum number L. The other is hidden in quantum number M. Fine. Of course, due to dimensional reasons, this fellow should be proportional to h bar squared, the other fellow to h bar. That is obvious. If they are common eigenvectors, then I have to reproduce these guys back. And now I could write here M and here L. Well, I know what are the results, and you also know what are the results. So it's better to write here M and here L times L plus 1. Of course, it does not tell you what are the permitted values of M and permitted values of L. Sure, yes? Any number that I have to put here, I can write this way. Okay. So imagine that I take my Lm state and compute mean value of the L square. Well, this fellow, on one hand, is due to these guys, h bar square L times L plus 1. But on the other hand, I can write it this way as Lx squared plus Ly squared plus Lz squared. Yes? Sure, L squared is sum of 3 squares. Okay, now, I think you understand that this number cannot be negative, yes? Sure, it's a positive operator, or if you want, I can take one of these Lx, put it on the left, and it will be norm of Lx times Lm state. So it's positive. Same thing here. And this is, of course, h bar squared times m squared. So if I drop these two guys, then I can only make right-hand side smaller. In other words, h bar squared cancelling, I have a very simple inequality. Yes? M cannot be huge. For given M must be within bounds. Yeah? Okay. So now comes this famous trick. Namely, we introduce two additional operators. We introduce L plus and L minus. And they are combinations of Lx and Ly, with plus and minus. Because of this I, obviously L plus and L minus are not Hermitian. But who cares? Sometimes they are useful. Now, I think it is clear that both L plus and L minus commute with L squared. Yes, because both Lx and Ly commute, so its combinations I are also commuting. What does it mean, and what is the consequence of this fact? Well, it means that if I take Lm state, and if I act on it with L plus or L minus, so I'm getting some other state, and then check what happens if I act L squared on this new vector, then because of this commutativity, I can pull this L squared through. I know that for L squared, this fellow is an eigenvector with the eigenvalue h bar squared times L plus 1. Yes. So I'm getting h bar squared L times L plus 1 times L plus minus Lm. Okay, that's very nice. It means that L plus and L minus is not changing L. Yes, it's also an eigenstate of the same, with the same eigenvalue. But what happens if I would like to act with Lz on this L plus L minus acting on Lm? Okay, to do this, it's good to know what is the commutator of L plus with Lz. Of course, L minus with Lz also. But let me do it very carefully. So this is the same as Lx Lz plus I Ly Lz. Yes? Now, what is the first fellow? Of course, it's proportional to Ly, but with what sign?
Minus.
Very good. So it is minus Ly plus I, and of course H bar is in front of everything. And Ly Lz, what is it?
Plus Lx.
Plus Lx, yes? Plus Lx. What does it mean? Ooh, if I pull...
Always multiply by I, if so.
Us. Yes. I here, and here is minus, yes? Right? Is that correct now?
Mm-hmm.
Good. So this is minus H bar times L plus. Yeah? Similarly, L minus Lz is what? Oh, very similar, except that there's a change of sign here. So it is plus H bar times L minus. You agree? I think it is correct. Good. So now I can do what I promised to do. Namely, I can take my Lm state, act, say, with L plus on it, and then check what happens if I write Lz here. Okay? Now this is nothing else but Lz L plus minus L plus Lz plus L plus Lz, right? Acting on Lm. This is a commutator. It's a commutator of Lz and L plus, so it is in different order. So this is H bar times L plus. Yes? And Lz acting on this is H bar M times L plus. Everything acting on Lm. So what I'm noticing now? Well, I'm noticing something rather nice. Namely, that L plus multiplying Lm produces again eigenstate. Why do I write omega? I don't know. Produces again the eigenstate, but with the eigenvalue m plus 1. Yes. So, we can write the following, that L plus acting on Lm is, apart from some coefficient, which I did not determine yet, is proportional to the next m of LZ. Very similarly, let me call it m plus, very similarly, same reasoning is showing that this thing is proportional to L m minus 1. So, I fixed m. I know that my m's are limited both from below and from above, because I had this inequality before, yes? So, if so, then by either acting with this fellow many, many, many times, I will finally destroy this inequality, because m squared will be larger than L times L plus 1, or acting with L minus and decreasing m, I will again blow the floor, so to say, by getting too huge, in absolute value, negative m. Yeah? Okay, what can prevent this? What can prevent this is presence of m max and m min. And both these guys should have the following property, namely that if I act with L minus on L m min, I'm getting 0. In other words, this funny normalization should turn into 0. And similarly, when I'm getting with L plus, then finally I should reach some m max for which L plus is just destroying it. Or if you want, for which the state is an eigenvector of this fellow with an eigenvalue equal to 0. That's the same thing. Okay. So, in order to find out what are these mean and max m's, let me do one more exercise. Let me write down L squared, which is Lx squared plus Ly squared plus Lz squared, in terms of these L pluses and L minuses. Look, if these x and y components were commuting, then this fellow would immediately become L plus times L minus, or L minus times L plus Lz squared. But this is of course not true, because when I multiply these guys, those other two terms are not 0. Instead, they combine into the commutator. Yes? And the commutator of Lx and Ly is, of course, I h bar times Lz. So what will pop up will be some additional term with Lz in it. And I will check how it looks without bothering you with this expert calculation. So when I have L plus on the left, then I get minus h bar times Lz. And if I have this, then I have, of course, I need to have plus h bar times Lz. So these are two equivalent expressions for L squared, which are kind of handy. Why? Because with these expressions, I can calculate norm, say, of L plus acting on psi. My psi is, of course, L and M. because this norm, which I have erased this, but it was this n plus squared, yes, is the same as L m, L minus L plus, L m, and now out of this I can express this L plus times L minus as L squared minus L z squared plus S plus, right? H bar LC, is it correct? Probably. Let me see. It is very nice because our state here is an eigenvector of each of these operators. So of course I get n squared. Sorry. So of course I get h bar squared times L times L plus 1 minus m squared plus m, which is the same as minus m times m plus 1. Okay, that's it. So similarly, L minus Lm, L minus Lm is h bar squared times L plus 1 minus m minus 1. Okay? Now it is easy to guess or to understand what is the value of L max. Well, L max is such m that this vanishes. Yes. And of course from this we immediately see that it vanishes when m max is equal to L. And by checking for which lowest m this fellow vanishes, of course we immediately see that m mean equals minus L. We are almost there, and of course we all know exactly what are the final results that we are going to obtain here. Look, we have minus L as minimal value of this projection, plus L as maximal value of the projection, and these L pluses and L minuses are jumping with my m by 1. So when I start from the very bottom, from this minimal m, I apply L plus, climb up. I have to get exactly to m max, because there's only one m max positive, which is solving my equation of the vanishing norm. Yes. In other words, from minus L to plus L, there must be integer number of units. Now, of course, the famous miracle of a spin pops up. Why? Because in order to satisfy this condition that from minus L to plus L there is integer number of units, it does not follow that L itself must be integer. Of course, if it is, sure. But also, if L is half integer, there is this integer number of steps from bottom to the up. Yes. For instance, if L is equal 1/2, then we have minus 1/2 state plus 1/2 state for the m. And obviously there is a 1 unit linking these two things. Of course, we are all familiar with the fact that angular momentum can be half integer. And we all know that electrons, protons, and neutrons are such funny quantities, such funny objects, particles that are having this half integer, what we call spin. Is it something which is really interesting and surprising? I think it is. Why? Because if I would use my Schrödinger position representation, then as we all remember, Lz is h bar over I times d psi by d phi must be equal to h bar m psi. The eigenvalue problem in Schrödinger picture, in Schrödinger representation or position representation looks like this. If there's only one variable of interest, I can put ordinary derivative. And of course, this equation has the solution psi equals some normalization constant times e to I m phi. And this, in order to be proper square integrable function on the circle, and also single valued function, then of course m must be integer. If m would be half integer, obviously it would not be a good solution for the spatial dependence of the wave function on phi. Therefore, in reasonably good textbooks, there is some strongly worded remark that the spin of the electron, or spin of the proton, can be viewed, can be visualized as the little spinning of a ball. It is not rotational motion of anything. Why? Just because of this. Has it been rotational motion of something, m would have to be integer. So L would have to be integer. Yes. I'm sure you probably heard this before, but let me stress it in a very strong way that this is really remarkable that this commutation relations for the angular momentum are more, so to say, general than the Schrödinger equation for angular momentum, because they have both these integer and half integer solutions. And reality, nature, is such that both type of solutions are actually realized in nature. Yes. So the Schrödinger equation itself is not really taking into account everything. This possibility of spin is not there. Probably some of you, or maybe all of you, know that there is another relativistic Dirac equation where the spin 1/2 appears in a natural fashion and is indeed completely distinct from the angular orbital angular momentum, from something which is spinning. Yes. There is slightly more abstract or mathematical way of telling what we have done here and what we found out here. Rotations form a rotational group. Mathematicians call it O3. Generators are forming these algebra of generators, namely these commutators of various components of L. And this algebra of the Lie group of 3 is really derivable from rotations. We did it, actually. However, the same algebra can be derived from another Lie group, which is called SU2. It's a different, it's a larger group. It has O3 as its subgroup. But the algebra of generators is identical. So by finding the spectrum of the algebra of the set of generators, we somehow simultaneously solve the question of irreducible representations of both groups. And some irreducible representations happen not to be representations of all three, but the other one. Yes. So there is a group theoretical way of telling, cheating in some sense, without going into details, what really happens. Yes. There are two different groups that have the same algebra, and one group is larger, it has more irreducible representations. Okay? So from this normalization condition, we can write explicitly that L plus acting on Lm, not only we know that it is proportional to Lm plus 1, but also we know that the coefficient here is a square root, apart from the unimportant phase factor, of course, is a square root of this fellow, L times L plus 1 minus M plus 1. It's a general formula. And L minus acting on Lm is H bar times also square root L times M plus 1 minus M minus 1 acting on L M minus 1. Now, in the very first lecture, I was telling you that if we really know everything about the operator, namely its spectrum and its eigenvalues, then we can write, then all information about this operator is hidden in the matrix of matrix elements. That's a matrix representation of a given operator. So now, in every box defined by L, by the way, dimensionality of this box is easily checked as 2L plus 1, yes. So in every such sub-box spanning this irreducible representation labeled by L, yes. So in every such box, our angular momentum operator, all three components, are represented by 2L plus 1 by 2L plus 1 matrices. Because nobody remembers all of them, but there's one representation which is so important that everyone remembers or should remember it, and that's a spin 1/2 situation. Just because the spin 1/2 is so common, just because so often do we encounter it. So, for L equal 1/2, usually people, if it is half, then people write S instead of L, and just convention, just to make sure that we do not confuse easily orbital with spin. Our S operator would be H bar over 2, that is obvious, H bar is a unit, and 1/2 is just this number, so it's good to keep it outside, times 3 matrices which are called Pauli matrices. And let's compute these matrices, it's very easy of course. One of them, SZ, is obvious. It is 1, 0, 0, minus 1, yes? If this represents 1/2 minus 1/2, and this represents 1/2, 1/2. Here is our L and M, yes. So then this is an eigenvalue with plus H bar over 2, and this is the eigenvalue with minus H bar over 2, so that's it. That's obvious. What are the other two Pauli matrices? Well, to do this, let's look at this fellow. This is Sx plus I Sy. S minus is x minus I Sy. And what is this, for instance, this S plus? Well, this S plus, I use now S instead of L just to stay with standard convention. Yes, it's the same thing. Well, we know that S plus acting on this fellow produces H bar times, you remember, square root of L times L plus 1. 1/2 times 3/2, that's 3/4, yes? 3/4 minus. And now M is equal minus 1/2. So that makes plus 1/2. And here was M plus 1. 1 minus 1/2, it's again another 1/2 times 1/2. 1/2. Of course, when we act on 1/2, 1/2, then we get 0. It's here, yes? Now this is very nice because this is 1. So in other words, S plus acting on this one is just shifting. Acting on the other, it gives 0. So S plus is H bar times matrix 0, 1, 0, 0. Yes? It's a matrix which takes you from down up. Same thing for S minus, except that it does exactly opposite. So it is 0, 0, 1, 0. Yes? And now by adding these things together and dividing by 2, I'm getting Sx. And of course I get H bar after dividing by 2 times matrix, which is the following. So sigma x, H bar half I want, is simply 0, 1, 1, 0. And very similarly, sigma y is equal to 0 minus I 0. I think almost universally, regardless what you want to do in physics, it's good to memorize Pauli matrices. They pop up so often, not even necessarily in connection with angular momentum. For instance, they pop up very nicely when describing polarization of electromagnetic waves, so-called Stokes vector. I'm not talking about details, but probably some of you encountered have seen this. Why is it so handy? Just because if you take 2 by 2 matrices, then of course there are 4 entries, yes? So viewed as the vector space of 2 by 2 matrices, you need 4 basis vectors to span every matrix with coefficients. Yes? Now these are 3, and they are really linearly independent, as even construction shows. And the 4th one is that fits here is kind of obvious. It's a unit matrix. So these 3 matrices sigma and unit matrix are forming nice 4 matrices that are universally helpful wherever you have 2 by 2 problem, whatever its nature. Of course, there are infinitely many choices, but this one is kind of canonical. It's typically the easiest to use. Good. Now, I will come now to the oscillator, and next week, these young heroes will be telling you or reminding you how to add to angular momenta. We'll tell you a little bit about Clebsch coefficients, Clebsch-Gordon coefficients, about 3J coefficients, and things of that type. Plus, maybe a little extra. But now I go on to the harmonic oscillator. Any question? No question. Things like crystal clear, I hope. Oh, before I jump to Harman later, let me tell you that just as a little exercise, derive these three matrices that are describing spin 1, or angular momentum 1. In this case, you have angular momentum proper. Yes. So there is also space-like representation of these eigenvectors. These Lm are represented in the Schrödinger representation by these spherical harmonics, YLM, yes. So for L equal 1, of course, these are the well-known functions, which you can even derive and look at and so on. I want something different. I want to use this, want you to use this algebraic approach to find out 3 by 3 matrices, three 3 by 3 matrices, representing L equal 1. Just to drive home my message, namely, that almost universally, practically in every application of angular momentum algebra, you do not have to resort to special functions. All you really need to know are how to handle these matrices. And that's it. So, the second example, and the last one, is the harmonic oscillator. So, now, for the first time, we are talking about eigenvalue problem for the Hamiltonian, something that is almost the most common problem in quantum mechanics. So we've got Hamiltonian, which is like this, plus 1/2 m omega squared times x squared. And to really use tricks which are analogous to the ones that we used for the angular momentum, I want to introduce two funny operators, A and A dagger, and just to make sure that I do not make mistake with coefficients, I will use my notes. So it's a square root of m omega divided by 2h bar times x plus I square root of 1 over 2m omega h bar times p, and the Hermitian conjugate guy, which is same coefficient times x minus I times 1 over 2m omega h bar times p. Okay, nice guys. The next, I want to compute most important commutator for this business. Well, I have to plug in this formula. Of course, we remember that x, of course, commutes with itself, p with itself. So all I have to do, I have to use the commutator between x and p. And the commutator of x and p is I times h bar. So this I use. There's also I always when I multiply x by p, so the result here will be real. And also h bar will cancel because h bar appears both times here in the denominator. The m omega will cancel because in one case it is in the numerator, in the other in the denominator. And this 1/2 will of course also combine into 1, and this way one easily checks this formula. It's very fundamental. It's also something that if you did not memorize earlier, it's time to memorize it. I would say every physicist should woke up in the midnight. No, he's never asleep at midnight. I should remember it. Okay, now, let's look at the Hamiltonian. Better, let's look at the product of A times A dagger. Well, I have to multiply these things. When I multiply, say these two guys, yes, this times this, then I get m squared. I get h bar, of course, and so on and so on. I get almost 1 over h bar omega times p squared over 2m plus m omega squared x squared. Almost a Hamiltonian, except that again, multiplying these two guys, since they do not commute, I also get a contribution from the commutator. And this contribution from the commutator has 1/2 in the denominator, and actually it is plus, how is it? 1/2 over h bar omega. So in other words, I'm sorry, minus. So in other words, my Hamiltonian can be written as h bar omega times a dagger a plus a half. Okay. Now, when we look at the initial problem, obviously this Hamiltonian is a positive guy. It's positively defined. Again, if I take some eigenvector and take mean value, then again, because I have p squared here and x squared here, I can always pull 1 to the left, 1 to the left, and I will get the square of a null, which is a positive or non-negative quantity. And therefore, if I denote by n some eigenvector of this Hamiltonian, again, without any loss of generality, I can write the eigenvalue in this form. Yes. So whatever n is, whatever the eigenvector is, certainly this is positive. In other words, this fellow cannot be negative. Good. So now, just as before, let's assume that I have such a guy, and let's assume that I want to know what happens if I take my as yet unknown eigenvector, multiply it by this A, which, anticipating your knowledge, I can call lowering operator. And if I apply now my Hamiltonian to this guy, this is also dead now, or half dead. Let's see. So I would like to compute this thing, and in order to do so, just as before, it's good to know the commutator.
Still 4 to go.
Yes.
Whoa.
The commutator of Hamiltonian with A. Okay, when I take my expression for the Hamiltonian, then this fellow, of course, commutes with this A. And that's not interesting. So what's interesting is h bar omega times commutator of A dagger A. Yes? Now, with the magic formula, I can pull A dagger to the right, to the left, and then, of course, this term is 0. or I can pull A to the right, and this term is minus 1. So in other words, the resulting thing is formula is minus h bar omega times A. By the way, analogously with A dagger, same thing, except that now it is in the right, so to say, order. So this is plus h bar omega times A dagger. Okay. So, I told you that I want to compute h, A on n, and in order to do so, I am writing h, A minus A, h plus A, h acting on n. This is my commutator, and my commutator is minus h bar omega times A. And this is, of course, eigenvalue n plus a half times h bar omega A. So in other words, A acting on n produces another eigenstate, but this time with the eigenvalue smaller by 1, yes? This combined is the same as n minus 1 plus a half h bar omega A n. In other words, A acting on n is again some normalization times n minus 1. Again, my trick is the same. I act with this A again and again. I lower this n by 1, by 1, by, and finally I must get 0. Otherwise I could break my inequality, which says that the mean value of my Hamiltonian must be positive. So there must be n minimum. There must be n minimum, n minimum, such that A times this n minimum is simply 0. Otherwise, I could go down as far as my wish. Okay, so let's take this state of minimal energy and act on this, with the Hamiltonian. My Hamiltonian, I hope, is still written somewhere. The Hamiltonian was h bar omega A dagger A plus a half. And due to the property of this n mean, this first term now vanishes, yes, because A hits n minimum. So in other words, this is exactly equal to 1/2 h bar omega times n minimum. First, we found out that the ground state of the harmonic oscillator has this energy. Second, we also found out that the eigenvalue, this n mean, is equal to 0. Because out of this general formula, we see that this is 0, yes. So in other words, there is the ground state, which is legitimate to call it 0, which has this 0-point energy. If someone has this instinct of masochism, then one can still ask, how does it look, this state? And it's very easy. You just take this operator, act on this unknown state, and equate this to 0, right? So in other words, the ground state wave function is satisfying the following differential equation. M omega divided by 2 h bar x equals minus I 1 over 2 m omega h bar times h bar over I times d psi by dx. And you see what I see, that probably I made some sign error here. Why? Because I want my solution to be a Gaussian with a minus sign. So in other words, in this equation, I need a minus sign here. So you can check. Maybe in the notes it is correct. I don't want to look at this. But now you see very clearly, yes, that the solution to this equation is of that type, yes? So one gets this famous Gaussian for free without solving truly Schrödinger equation, but just looking at what is annihilated by the lowering operator. Okay? Now, very much like A shifts our energy one step down, a dagger, if I act with H and again use the commutator, shifts the energy one step up. N plus 1 plus 1/2, a dagger, and yes. So this fellow is again eigenstate, but with an eigenvalue which is higher than the earlier 1 by 1. So now it is obvious what happens. There's only one state which is annihilated. That is the state which has eigenvalue 0. And I have a whole ladder of states that are going up by 1. And that's the quantization of the energy, right? Every state now must correspond to n equal integer. 1, 0, 1, 2, 3, 5, up to infinity. It cannot be fractional. Why? Because if I had something fractional, then I could go down, 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 and again exceed my inequality. I have to hit 0. Yes? Because that's the only state which is annihilated, which has the lowest energy. So in other words, from this reasoning, we figure out that n must be integer, 1, 2, and so on. There's one more thing before we speak, and namely we have to compute the normalization coefficient. We have to figure out what's the value of this fellow. Yes. Well, this is how it goes. We shift like this. Sorry. A dagger, A, N, yes. And then use the Hamiltonian, assuming that, of course, these guys are normalized. And this way, we get that A acting on N, of course, is proportional to N minus 1. But proportionality coefficient is square root of N. If we do the other way around, if we take A dagger N, A dagger N, then this is the same as N, now A N plus N. And here, perhaps we don't know how to use the Hamiltonian, but again, we add and subtract A dagger A. In one step, we use the value of the commutator, this unity, and the other just like that. And then we get, instead of n, and after that square root of n, we get n plus 1. So A dagger acting on n is square root of n plus 1 times n plus 1. So these are also two formulae which I would say typical physicist would know by heart. And you probably can also memorize this formula very easily. Once again, next week these guys are telling you about adding angular momenta. If they have time, they could tell you a little bit about coherent states. So they can elaborate a little bit on both parts of this computational part of the lecture today. And 2 weeks from now, we come back here, and I will be talking about interpretations: Copenhagen, Everett, Feynman, David Bohm. I don't know any other. Well, there is one more, but I will not talk about it. There's some funny interpretation in which one is thinking of physical objects, some of them going forward in time and some backward in time. And during the measurement they meet. I think it's so crazy that I never really understood what it is.
Who is the author of this?
I don't remember. But there is a school which believes in this funny interpretation.
How do we know that?
It's a little bit about, yes?
How do we know the generation here?
Yeah.
So we know that there must be a grand state, but maybe
By acting no, there's only one ground state.
But maybe there are a few successive states in one level.
No, because if I had some other state and go down, I have to come back to the same fellow.
Yes, but
And there's only one, so to say, ladder.
At the beginning we assumed that A dagger A, I think that there is only one eigenstate with eigenvalue n of A dagger A.
Well, is it really an assumption? I don't think so.
No.
I think it is, in some sense, obvious. It's a one-dimensional problem.
okay, we have constructed an operator and checked what is the solution
Yes.
to the eigenequation.
Yes.
And it was only one solution.
Yes. Of course, one can always refer to the Schrödinger equation for this, where there is also only one square integrable solution. The other is always blowing up and infinities. But this has no counterpart in such algebra. This other, so to say, wrong solution has no counterpart in our considerations because we are in the Hilbert space from the very beginning till the very end. In other words, I could write one more formula. Since I know that A dagger is increasing, then the n guy I can always write in the form this divided by n factorial acting on this. There's only one such state. In this algebra, I have no other object, yes, except A dagger, and Hamiltonian. So I have no room for any other state. In order for this Hamiltonian to be degenerate, somebody would come with another commuting operator, which is not a function of Hamiltonian, which is commuting, so there is a common eigenvalue, a common set of eigenvectors. And there is none if I have only 1 degree of freedom. In 2 or 3 degrees of freedom, there is, of course. Because if I write my 3D Hamiltonian in the form of x plus y plus z, and each of them is also harmonic oscillator Hamiltonian, then the species are commuting. And in this case, of course, I have common